Hello there. Just wondering if anybody's there. If you are, please put a chat in. This is just a light review of what's going on right now. What I'm going to be doing is I'm just using this as practice. I'm going live, as they say. I'm going to just try this out. No camera accepted. I'm just doing slide views and so forth. The goal is to just show off. Well, I guess I am down in the corner. Isn't that nice? So there I am. The cat's chair is there. He might join us. If Cosmo does join us, I will let you know, and you'll probably know anyway. So I'll show you what I should probably do is I should probably migrate this over here because it doesn't make any sense for me to do it that way. So I will just put my slides on this screen because that might help things. That will be better. Okay. All right, hide this presenter note so I can actually begin. Well, that's yucky. What the heck's going on there? Correct. I'm just going through this thing really slow. Please forgive, because I'm just trying this out, just to see what it's like. Hello, good to see you, Luxfer. Glad you're here. Yo, glad you're here. I'll try to keep that right there, and I'm going to try to talk into this area. Hope you can see everything. Cat's going to be around. Let's see what we got. 2 concurrent viewers. That's pretty nice. So, okay. This is the first time I'm trying to do any kind of live streaming. I'm just seeing how it goes. It might be kind of fun. I've got my Soba Cha tea. The cat's over there. I'm here in the new place in Chicago after having moved around a lot from New York to Albuquerque, now to here. Cat will probably join us, especially if I bring out something crunchy. So what I want to do is I want to try to go over the upcoming video. I just want to practice it before I do an actual live run. So we can look at what we're going to try to do with this last thing is actually discuss the proper distance. Well, why am I doing this? It's good to see that particular message around, but I've been just trying to do this for a very, very long time, as you've seen. I've created a lot of videos in the past. I've had some. It's been a bit since I've been able to do any, but that's okay. You know, life is life, and that's just the way we go. So, what I wanted to do originally is try to go through the entire textbook of Barbara Ryden as an introductory cosmology textbook. But of course, since I started this, there's been so many incredible changes in the world of cosmology that it's really hard to summarize it all. However, we still need to understand some of the basics of the mathematics and so forth. So if you watch the previous videos all the way up, you're going to get there. Now, we're going to need to talk about the nature of how the Hubble tension is changing a lot of things. That is definitely something we're going to have to talk about later. But I'm going through the fundamentals so that you can understand why their changes are the way they are. Okay, I'm also watching the chat. My chat's right there. So if you do have a question, please just jump in. I'd be glad to answer questions as we go. This is just casual. I don't know how long I'll do this. It is a Thursday night, and it's cloudy outside, and I do have to get to work in the morning. So we'll just see what we do. So this particular study of cosmology has been interesting to me for a very long period of time. Actually, Luxfer, please give me a thumbs up if you're still listening, or if anybody's listening, and if you can, please give me a thumbs up or any kind of emoji if the microphone is just fine, because I cannot tell. I don't have headphones on, I don't have a studio speaker or anything, but if you can give me a shout out to make sure that this actually sounds good to you, either hit an emoji in there. Fantastic, thank you for the okay, thank you, Kayak 12, thank you, fantastic. Okay, just let me know. Okay, there's a good little rabbit. I like the thumb, the 2 fingers. Fantastic. Thank you, Luxfer. Excellent. So I'll just keep going. But please interrupt me with questions in the chat. I will do my best to keep my eyes peeled on it. Okay, so there's a lot of things that go on with respect to cosmology. It's been interesting to me since I was a little boy. I think I got into astronomy because I wanted to know how the universe worked. And I thought that I could learn all the maths and I could learn it all. And if I learned cosmology, then I've learned everything. What I learned is that as over time went on, is that immature view that I had as a little boy, I'm talking about a really little boy, grew up to actually appreciate this for what it really was. It is an amazing mathematical study that became a physical science. And this physical science is really the thing that underpins some of the most interesting and fundamental ideas of modern thought. And it's amazing to try to wrap your head around them. Cosmology has supplanted philosophy for its metaphysics. Metaphysics used to be the area of it. But if you were a philosopher like my cousin Monty Link over at Boston University, Monty really loves this stuff. And so we occasionally chat about it, and he's all jealous that I do cosmology-related videos and have taught astronomy, but he's a tenured faculty at BU in philosophy. So, he's writing books. So that's great. Anyway, thanks for the soothing voice. Thanks for that. My wife says that I have a very soothing voice, and that's nice to hear. So it's nice to hear from you too. Thank you. All right. So I don't know if you had a chance to watch the other things, but this is a kind of a raw view of what I want to try to work on as a full view in a future video that I record. Usually my process is I create all these slides, and then I write some sort of general script, and then I read it, as you can probably tell by how I'm speaking now. I do kind of go back and do a lot of edits. I've been noticing that if I do too many edits, I sound like an AI bot or something, and that's not the intention. I didn't like a lot of my early stuff because it was terrible audio, but it was passionate and having a great time, and it was teaching and having a good time. So let's see what we have here. In this chapter 3, section 6 of Barbara Ryden's Introduction to Cosmology, she discusses the concept of the proper distance. And proper distance is a really funny term because there are lots of kind of distances in cosmology. And so what we need to do is we need to understand what proper distance is and what we mean by that, and what proper distance can be, and what distances are in general. All right, let's just click through. Great. So this is of course my fun slide, my summary slide that one day I should turn these into posters. I think they'd be great posters. And I think all I have to do is just expand them and send them off to someone to make them really poster size. But I think they'd be really fun for like schools and such. It's like, oh, this is crazy. A whole lecture in a poster would be great. Okay. And I just want to say thank you, because obviously you're subscribers. So thank you, subscribers, and thank you, Patreon members, for helping to support through all these times and years. It's great. Fantastic. So let's continue. There, of course, there's my Patreon channel. Please do subscribe to there, but not just yet. I want to try to build some stuff up. So got to get back into it. Anyway, what is distance? So let's talk about distance. And we can think about distance in a lot of different ways, but we tend to think of distance as I am here, it is there. And notice how I phrase that. I am here, or this is here, and that is there. So that is very important. And what here means and what there means is also really important for cosmology. And so when we're on the Earth, we think that everything's on the Earth, and the Earth is mostly a fixed object, not in the space, but in terms of stuff. Over human life scales, we shouldn't expect a lot of things to change. I mean, sometimes there's an earthquake, stuff like that. But, and sometimes there's a disaster or a landslide. But typically, a lot of things don't really change. So when we think about distances from X to Y, or from hither to thither, or yonder to near, we will measure them by using, say, a standard ruler. And the standard ruler is the way that we tend to think about every kind of distance. It's like, take a stick, put it on the ground. How many sticks does it take to get over to that far mountaintop? So the meter is just one definition. There's so many ways you can define ticks on a stick, and then say how the ticks on the sticks are the fractions of the meter or foot or yard or furlong, or however long you wish to go. Now, there's another way to measure distance. You can say, how long does it take for me to get there, given that I go at a given speed? And so the transit time might be It might be to say, okay, it's twice that distance because maybe you want to take a pigeon and the pigeon flies to the top of that mountaintop and then flies back. So assuming the pigeon flies at the same speed the entire time, half the length, half the time it takes, or is the distance. So it'll go twice the distance, and the round trip time will give you the distance. So the transit time going back and forth, the pigeon from you to the top of that mountain and back. The other thing you can do is you can put a bright light on top of that thing that you know exactly how bright it is. So the brightness B, and the luminosity is how bright it is. Maybe it's a 10,000 watt candle or something like that, or whatever it is, standard candle. You call them candles. That's just very traditional. We don't call them standard light bulbs or standard flash bulbs or something. They're a standard luminosity source. So if we know what that luminosity is, L, and we know how bright we perceive it to be, which is that letter B, then all we have to know is that that luminosity gets spread out spherically away from that distance by 4 pi d squared. And that the brightness times that gives you what the luminosity is at the source. So if you know how bright it is at the mountaintop, and you know, well, what its output of energy is, luminosity, and what the brightness is that you see it at, B, then 4 pi d squared is the distance. That d is the distance from it. Next thing we could do is simply do an angular size distance. If we know how big a feature is on that mountaintop, let's say that ridge that we see running right below the letter is, right between is and that up the top, there's that little great ridge right down from the top of the mountaintop. That's a ridge. Maybe that's a half a mile long, and it's at a 30-degree angle. So you can guess how long half a mile is at a 30-degree angle, and that tells you a physical size to that thing. Now that physical size then has an angular size, and that angular size is theta. And so there's some height, h, and then there's that distance, how far away it is. So we know that that ridge was half a mile times cosine of half a mile. What would be sine? Yeah, because it's like this side, so sine would be up. So we go like that for the triangle. So we have the height of the thing that we see on here, which is this, but it's actually this long. So there's an angle here. So we know what the exact size of that ridge is. So the height of the ridge divided by the distance equals the tangent of the angle that it subtends in the sky. So it's a very small angle, and it's a very big thing. So the farther away something is, the smaller it looks. And that's what the angular size distance is. Next, we could do trigonometric parallax, which we don't see in this particular picture, except if we thought of ourselves as being on one side of the valley and then going down to the river and then on the other side. And now we have some baseline between them. And so the baseline would be one baseline. Now I'm using the stellar parallax method right there, but let's call it one for the trigonometric parallax, one baseline distance. And the parallactic distance is the angular shift compared to some really distant background thing of that mountaintop. We don't need to see other mountains in the backdrop, but pretend there are. So then there would be some angular shift of that distance from with respect to some farther distant mountaintop, and that is parallax. So parallax very simply is you take your thumb at an arm's distance and blink your eyes back and forth, and the angular shift of your thumb with respect to the distant thing in the far, which is for me the computer screen, that parallax distance shows the farther away it is, the smaller the angular shift, the closer it is, the larger the angular shift. That gives you the trigonometric parallax, which is critical for astronomy. Now, the fun thing is that you could also have a standard sounding chirp, which is sonar or gravitational wave. So something where you know how loud it is, what the volume is or intensity of radiation in terms of sound waves. And that standard chirp will decrease in intensity over distance, very similar to the standard candle. Now it's of course more complex if you have air and there's different media through which the sound is traveling. But that's how dolphins communicate. They use echolocation, so the bats. We can use sonar to plumb the depths of oceans, and gravitational waves can be measured to have a standard chirp from colliding black holes. So there's lots of ways to get distances in this peculiar way. But all of them, every single one of these things, depends on the Earth or whatever you're standing on to be a fixed thing that you measure on the surface of things. So that is important for this, because all of these things are determined to be how far is something from me to there. And the distance doesn't change as you measure it. And it's also physically possible to do any one of these measurements to that far mountaintop. It might take you some time, but you don't expect the mountaintop to run away, change in the time it takes you to get from this valley to that top of the mountaintop. It's just going to be like you plant the flag here, you do a walk, and it'll get you to the mountaintop. So let's look at what we mean by all of these distances. Next, we have the very simple distance of measuring by a ruler. Yes, of course, this is an AI-generated image. I just love it. It's so funny that this imagery is so. All you have to do is type into your standard ChatGPT, show me 2 college students measuring sticks on a ground. I didn't photograph anybody like this. It just seems weird. But anyway, wonderful stuff. If only college students would measure sticks on ground with such intensity and not actually stare at the thing they're looking at, because that's how you know it's AI-generated, because she's staring at that funny leaf on the ground, and so is he, but they're measuring things between a leaf and a stone. Very silly. Anyway, you can do a physical distance using some standard ruler and just keep placing ruler after ruler after ruler, and you could have gone, you can do this a lot. And I seem to remember a very long time ago when I taught briefly at a middle school in New York, and I saw these little kids on the sidewalk doing just this, measuring the length of the sidewalk, as their science teacher told them to go do this. I was teaching math at the time. And the kids were measuring the sidewalk. It was so cute. They had little clipboards and everything like that. But yes, this is one way to measure your distances. Then the other way to do it is to run fast. And so here's me running race walking. I don't run anymore because I have both my knees replaced. But I race walked the 5K in Governor's Island, New York City, and that was wonderful to do. I think I did that one in 34 minutes. So I could say I did 34 minutes at 5K, and I know what my pace is. And I knew that my pace was 11 minutes and 40 seconds per mile. So I didn't even have to know that it was a 5-kilometer distance. Because I go at an 11-minute 40 pace mile, that means that when I got to like 34:50 or so, is that right? No, 33 plus a minute and 20. Yeah, 34:20. Once I got to that, I'd known that I'd gone a 5K. So the transit time measurement is how long did it take to get that distance at a given speed. That's transit time. Next, we can look at simple luminosity. And luminosity is a luminosity distance, or a brightness distance, says the same candle perceived at different distances. Says it's the same candle, perceived at distances will be perceived to have different brightnesses. So stop me if you have any questions, please do, or just say, hey, thanks for being here, or something like that. And I just want to say, shout out. I'm going to take myself away for a second and look at the chat and say, thanks for being here. I know this is some other concurrent viewers. Great to have you along. I'm talking about talking about Barbara Ryden's chapter 3, section 6 about proper distance. I'm just doing my notes on proper distance. So check in if you'd like and say, give a thumbs up, something like that. That'd be wonderful. Anyway, off we go. So what we mean by this brightness is, so the candle's emitting so many photons per second. And that is its luminosity. And each photon might have energy. So luminosity is a measurement of energy per second, and it's summed over all the photons that come out of the candle. Okay. But what we have is that we can put up a plate, a standard area, which is up in the upper left-hand corner, a unit 1 area, right? And that unit 1 area might get 16 photons passing through it, whatever. We're just making this number up. This is all made up numbers, right? So that unit area might get 16 photons through it. But at twice the distance, there is 4 times the area away from that. So that means that each of those individual areas, now there's 4 of them, so the 16 photons get divided up into 4 equal packets. So only 4 photons go in through an individual area of the same size that it was at part 1. Now, if we go 3 times distance, it's divided up into 9 groups. If we go 4 times the distance, it's 16 groups, right? So by the time you get up to 16, I didn't do 9 because who wants to do, partial photons, right? But once you got to 16, at 4 times the distance, 1 photon goes through 1 area. So you could say the dimming or the perception, so brightness is a perception or what you perceive it to be, right? It's not how bright the candle actually is, it's how bright it appears to be. And so we only get 1 photon, so it is 16 times fainter than it was if you were 4 times closer. Just means it's the same amount of energy, it's getting spread out over a larger area. And that is the luminosity distance or brightness distance. Next, we can look at the angular diameter distance. And I love this picture. This is a great picture taken, I think, by Babak Tafrishi down at the European Southern Observatory. And that baby is not just this is not AI. This is a fun picture of a little baby taken very, very low and apparently looking down into a telescope. Well, the angular distance to the telescope is far because it is large. Its size is large. So for the angle for it to be subtended to be roughly the same size as a baby means the distance has to be far. The baby, well, not really a baby, it's a child. The child size is small. So to have roughly the same size, angular size as the big telescope means it has to be closer. And that theta, tangent of theta, which is the opposite distance, which is the height, divided by the adjacent, which is the distance on the bottom, a dashed. So the hard blue line is how tall something is, the size, and the dashed line across the bottom is how far away it is, how far you have to walk. And of course, that's just standard trigonometry, which is always fun. Oh, did the cat jump into the chair? Yes, he did. Isn't he a good boy? He's sleeping right there. There's the Cosmo cat, Cosmo, of course, right? So that's angular diameter distance. Let's see, I think this is actually a movie I want to show. Oh, that's fun. So this is actually a well-used idea. Aristarchus, back in 200 BC, noted that the sun and the moon have the same angular size in the sky. He also noted that the moon goes in front of the sun, but the sun never goes in front of the moon, so therefore the sun has to be farther. Well, the ancient Greeks also knew that the moon's shadow was only so big. So they knew how roughly big the moon was by its shadow, and so they could determine that that the sun must be very large because of the shadow of the moon that we see of the moon on the sky. And they got the shadow by saying, during an eclipse, how long does it take to go through an eclipse or through a lunar eclipse as well as a solar eclipse? And that gives us the time. Usually it's the lunar eclipses that show us the size of the moon, the Earth, compared to the moon, which is they knew. So they could actually determine roughly that the sun was extremely big and very far. So Aristarchus knew that the sun was much, much, much bigger. Now, one could think that this is early science, and that's kind of a funny way of talking about it. Like, oh, the ancient Greeks, they were all scientists. I said, no, the ancient Greeks thought that the sun should be at the center of the cosmos, not because it has this greatest gravity, but because fire is nobler, and therefore the element must be at the center. That was their argument. It's not science, it's philosophy, and it's more like animistic philosophy and ancient Greek philosophy. So they did not have telescopes in order to determine distances and so forth. So that's what we've got with Aristarchus, but it's an angular size measurement to show relative distances. Again, angular distance becomes very important. It's the most important thing in elementary astronomy, and it's parallax distance. Parallax distance depends on a baseline between 2 observation points, and you can then, nobler, yes. Nobler is still very romantic, and we think that the sun is quite noble, and if you haven't seen Project Hail Mary, there's a little bit about the sun in there, and it's like, I don't think the little critters could live that way, so hey. Yes, I do think it is a very romantic notion, but but thinking about romance, though, romance was nothing that the Greeks would have known about because romance comes from Rome, so it is of and pertaining to the lifestyle of Rome. So a romance is a story of Rome. So this is not a Greek concept, romance. They didn't have that. There you go. How's that bite you? Anyway, so we keep going with it. The parallax distance, very good. The parallax distance requires a baseline to get a distance. So you have some distant tree with other big trees in the background or a mountain or something like that. And the angular shift, theta, again, that the tree does when you look at the baseline, when you change the baseline, gives you the distance to the tree across some impassable thing like a square lake, which you could have walked around, but we're pretending that they're the edge of the cosmos because you see stars off the edge. Like these guys don't want to walk off the edge of the lake because they'll fall into the stars. Remember, it's turtles all the way down. So so we can look at different kinds of size measurements. Look at that, the circle on the left. The theta can measure lots of different things. It can help us measure the straight up and down line that makes the triangle, which is the Harvey blue line, the green chord that goes from 2 points along a circle, and then the arc, which is the red arc of the circle. Now, if that angle theta is really small, then all three of those lengths get nearly the same. And that's a key element of parallax distance. Okay, what do we mean by nearly the same? The definition of astronomical parallax starts with the Earth and the Sun. The Earth is going around the Sun, and as it goes around the Sun, we can look at a distant star for between an interval of 6 months, and it seems to shift with respect to the background stars by some angle. And that angle, half of that angle, is called the parallax angle. Not the full angle, but it is basically a triangle based on the Earth at one place, the Sun here, and the star there. So the parallax angle is half of the shift, in the maximum shift in the sky. Now, parallactic angles are really small. So the parallax P angle, not theta anymore, but P for parallax, is the tangent of the parallax is very, 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 very numerically close to the parallactic angle itself, with very small numbers. And I'll show you what that means in a bit, but the most important thing is that we have to measure the angle in a very special way, and I don't know if I have that in the future. I do have it in the next slide, what that angle is. So we can define the parallax distance in terms of what we call parsecs, or astronomical units. So the distance of the star in astronomical units, where the Earth-Sun distance is 1 astronomical unit, the distance to the star in astronomical units is the parallax angle. That's its definition. But we then define the thing called the parsec, the parallax of 1 arc second. It is the most important fundamental distance in unit of astronomy, and the parsec is equivalent to roughly about 206,265 astronomical units. And where does that number come from? Well, there are 360 degrees in 2 pi radians. So there's 2 pi radians around a circle. And whoa, hold on a second. I don't think I defined a radian. Here's a trick. Notice on this circle, this line, the radius of the circle from the center of the circle to the circumference. Take this little red line, which is a radius, and project it onto the circle. That has a distance of 1 radian. And so we can define an angle of a radian as the angle that is subtended by the radius on the circle. The radius of the circle, the radius of the circle on the circle, as a chord, the red arc. So the angle of the red arc, when the red arc's length is the radius of the circle, is the definition of a radian, okay? So if we measure angles in radians, then we say that 2 pi radians is equal to 360 degrees. So we have a ratio there. There's 60 arc minutes in 1 degree, so we get rid of the degrees as a unit. There's 60 arc seconds in 1 arc minute, so we get rid of the arc minutes as a unit. And if we divide that out, we see that there is that there are 206,265 arc seconds in 1 radian. So if we then say, what is the parallactic angle in radians for 1 arc second? That then is 206,265 of the radial distances. So in order to make the arc length on the circle equal to one of those, what's the distance for, so that it's the same as 1 arc second? How far away does it have to be? It has to be 206,265 radii away. And that's where the definition of the parsec comes from. That's equivalent to 3¼ light years, and it's equivalent to 3.1 roughly times 10 to the 13th kilometers. So I always trip students up when I said, oh, what's the definition of parsec? I would say it's the parallax angle of 1 arc second. And then I would also put on the test 3.26 light years. And people would make the mistake of saying it's 3.26 light years. It's not the definition of the parsec. The definition of the parsec is an angular base distance based on the length of the Earth's orbit, the radius of the Earth's orbit, taken out into space until it subtends the angle of 1 arc second. That's the definition of a parsec. That's far. And here's the thing. There are no stars within 1 parsec. They're all farther than the parsec, every single star. So that's a far distance. 30 trillion kilometers is a very great distance. And for good thinking, here's another thought. The Voyager spacecraft, I think, are approximately 36 light hours away, and they've been sailing since the 1970s. The long distance. And the distance that the Artemis crew went was only 186,000, only about 200,000 miles, right? So they went only a few light seconds away. That's why there was a delay. It wasn't just that there was like communications problems, which, you know, they had a couple, but not any big ones. It's that there's a transit time to get signal from the Earth to the moon, and it's about a second. It takes about a second for light to get to the moon and therefore communication. So there's the definition of parsec. The parsec is the most important distance measurement. It is a physical distance measurement in astronomy. But that doesn't relate to cosmology yet. All right. So frequently then we come around and say, why not use light years? Light years make more sense. It's how far light goes in a year. Sure, that's nice, great. But how do we know how far light goes in a year? This is a kind of interesting philosophical question. You say, remember I was saying I knew how far I ran because I started at the starting line of the Governor's Island run, and I went for 34 minutes, right? 34 and a half minutes. And I knew what my time was, so I learned what my distance was. I wasn't traveling, I was traveling Jason half hours, right? That's what that is. So why not use Jason half hours as a standard unit of distance? It's the same thing as light years, which is the distance light travels in a given time, a year. Well, the thing is that light's a photon, and photons don't carry clocks. I was wearing my Apple Watch, so guess what? I could time it. No big deal. I have my Apple Watch at the beginning, I have my Apple Watch at the end. I can make a marking, I can make a marking on the ground. I can say, this is where I started, that's where I ended. Photons do no such thing. They have no such capacity. For them, when a photon leaves an atom, it's like a hydrogen atom is an excited state, and it drops from the excited state to the ground state and emits that light. That light goes from that distant atom all the way to us, maybe 10 light years away, oops, and then gets to us and gets reabsorbed by another atom. When that happens, to the photon, it was, I'm in an atom, I'm an atom, I'm in an atom, I'm in an atom, I'm in an atom. It never moved because the distance that it goes in space-time is null. Photons and light travel in null space-time metrics, which means that they do not have any, that when you go at the speed of light, you have no perception of time or distance, which is interesting. But that's why things that are physical, like mass-based things, can't go at the speed of light because they inherently can feel the effect of time. Photons do not. So why not use light years? Well, it is principally a wonderful way of discussing it because we do think about these kind of ways. We do say, how long does it take for you to get downtown on a bicycle? How far is that to drive, right? So we think in terms of I'm going from here to there. So it's a very, very, very nice way of talking about things, but it has almost no meaning in astronomy. And in fact, it doesn't mean it's hard to make it mean something, but it's a useful thing for nearby things. Once you get really far, cosmological distances, light years, are even worse. So, and yes, I had to throw this in there. Very old stuff. We're almost getting to the, wow, is it going to be the 50th anniversary of Star Wars? So if you go back and watch that, he did something in the turn, like a measured time, like light year. I did the Kessel Run in 17 light years. It's like, okay, good. I'm glad you did the Kessel Run in 17 light years, because guess what? That's how far the Kessel Run is. It's not a time unit, it's a distance unit. So the parsec is more natural as a distance indicator than the light year. However, it's really difficult for science communicators and people in newspapers to use parsecs, because we don't, as humans, very often go, how far is it to downtown? Oh, about 6 fingers widths, right? We don't use, oh, let's parallax my way downtown, you don't do that. How far is it to the next block? 4 thumbs, right? You don't do that. So that's why we don't use parallax, because we don't tend to think in frameworks that make sense for us to use parallax. Onward we go. However, when we start looking at stuff, we can say, all right, we have another time of transit distance. So how do we get the astronomical unit? We get the astronomical unit by saying, let's bounce radar off of Venus and see how long it takes to get back when Venus is at particular locations in the sky. The simplest method is to say, when Venus is at quadrature and it's at 90-degree angle, then you see it have one half illuminated. Then the setup in the sky is that Venus is at quadrature or at 90-degree. There's a 90-degree angle between when you're on Venus looking at the sun and the Earth. So they're 90 degrees apart as viewed from Venus. So we have a 90-degree triangle with the right triangle as the green bar, the distance between the sun and Venus, the blue, and the distance between the sun and the Earth is red. And we measure the radar distance using round trip time on the yellow from the Earth to Venus and back with a very powerful radar, such as the Millstone Hill Radio Telescope over at MIT. So they just beam and bounce it back, and Venus is very reflective because of its clouds. And so radar measurements are quite easy to do on Venus. And you can do this, you don't have to do it at quadrature because you can use trigonometry, but the 90-degree angle makes it just simple to understand. But this is a standard way that we find. This is the way that the astronomical unit was measured originally. All right. So we have got our basics. Again, it's parallax to stars, and how much an astronomical unit has been known and measured, and now we have a way of stepping from the astronomical unit out to the stars using parallax. But how do we get further? The extragalactic distance ladder, these are all the possibilities that we can use to get to cosmological distances. And so we have to stack these various measurements up, from globular cluster statistical parallaxes that are for nearby thing, and our Lyrae BW measurements, which are another statistical measurement. Cepheid BW, I'm going to have to go back and make a good video about all of these. But each one of these steps, how bright a globular cluster is, how bright are our Lyrae, how bright are Cepheids at their peak, how bright are standard stellar novae or galactic novae, the statistical parallax of large numbers of our Lyrae, the globular cluster luminosity function, which is how bright are globular clusters given their current spectrum, the tip of the red giant branch, and then going up the blue side, all the way up the blue side, then you have the DN sigma relationship, which is the statistical spread of elliptical galaxies that give you the distance based off of dispersion of the velocities that are measured of stars and distant elliptical galaxies. Then you have on the right-hand side in the green, the Cepheid variable bases, which you can calibrate the Cepheids that are in the Milky Way to get to the Large Magellanic Cloud, which then gets you Cepheids out to the local group of galaxies out to well past Andromeda and everything within a couple of kiloparsecs. And then finally, you use these to try to find, if you once you've calibrated the Cepheids, you hope to find a Cepheid in a galaxy that has a supernova going off, right? And I get the supernova 1A argument, which says a nearby galaxy, you can get the brightness profile for supernovae, and that gets you the step all the way out. So each one of these things gets you distances from here to here to here, and each step calibrates the previous one. And Tully Fisher is an interesting one. That is the rotational speed of a spiral galaxy. And the larger and more massive the spiral galaxy, the faster it spins. So that is a standard candle itself that starts at these high levels. There's also the planetary nebula luminosity function, which is the red one, and a specific maser interface, maser illumination, I think in a core of a galaxy, NGC 4258. All of these things allow us to calibrate the Hubble constant, which is the rate of expansion of the universe. All right, that's how we get out to these distances. And the Hubble constant is something that we have to use on the largest size scales, because galaxies become so distant that we can't pick out any of these things. They just become little dots. So once we get out to these very great distances, we are now completely dependent upon the redshift and the Hubble parameter in order to get us distances. But we've just introduced something very new when we said the Hubble parameter. All of these other extragalactic distance scales, they do not take into account what we know to be true, which is the expansion of the universe. They just tell us that the universe must be expanding. They derive the Hubble constant. The Hubble constant was a discovery because the Cepheids were known to be a certain brightness, but yet they appeared to be dimmer because the universe is rushing away from us. That's interesting. So I discussed that in previous videos, and I'll discuss it ad nauseum in other videos as well. So when we look at the distances on cosmological size scales, we have to now take into account this new parameter of the universe expanding, so therefore everything's sliding out from underneath us, right? It's kind of crazy. So what we get is we have to use the Friedman, Lemaitre, Robertson, Walker metric. And this is the homogeneous and isotropically expanding universe with the isotropic expansion, homogeneous expansion, and either expanding or contracting. So this is the metric for that. ds is, of course, the actual space-time distance, and it is a measurement of time, which is the dt, a little interval of time. dr, which is a radial distance from us with respect to us, the observer. And the d omega, which is the big omega thing at the right-hand side, that is an angular spread across the sky. So this particular thing shows how those the hyperspherical coordinates that Ryden uses, which I discussed in previous videos, are dependent upon the radius curvature of the universe and the distance, right? That's what that function S sub k of r is all about. And it depends upon whether or not the universe is flat, k equals 0, or positively curved, k plus 1, or negatively curved, k minus 1. And the kappa values, plus 1, 0, or minus 1, or whether it has that kind of curvature. And the radius of curvature is the big R inside of the SK sub little r, where little r is the distance we're measuring to the thing. Now the space-time distance, ds, is really what we're measuring. That's our real measurement out to the cosmos. It's not dr. dr is the spatial part of the metric. ds is the actual space-time distance, which takes into account the expansion as well through time. And that A of t is the scale factor by which the universe is expanding. How fast is the scale of the universe expanding with time? So there's our metric that determines how the universe is behaving. And all the physics that everybody's talking about, doesn't matter what you're doing, whether there's dark energy or matter or dark matter or scrimblat with cheese on top, that's going to influence how A of t goes with time. And what that big R is and what the kappa is. So you've got the big R, which is the radius of curvature, the kappa, which is the kind of curvature, and A of t, which shows how that changes universally and homogeneously and isotropically with time. Great. So when we wish to actually know the distance to a thing way over there, we only care about the distance to a galaxy. We're not trying to say how far it is left and right. So we don't care about the angular spread across the sky. So we're going to cross that out. So we're going to try to get this distance to a distant galaxy. We're trying to get that ds. So we first cut the d omega because we're referencing it from us to a distant galaxy. And that distant galaxy is a linear direction over there, not, we don't care about the side-to-side part of the metric. It means if we have to go left or right, we don't care about that. Next, we wish to do a funny trick. We're going to pretend that the universe, we're going to fix the scale factor. I mean, we're going to freeze the universe. We're going to pretend for a second. This is really important pretend, the most important pretend. We're going to pretend that we can freeze the universe and lay down a bunch of meter sticks, just like our college students doing over here. The universe is frozen, just like they are, and we're setting down a whole bunch of meter sticks in order to get all the way out to the cosmos, right? So we're fixing the A of t at a given time. And so therefore there will be no change in time. That's a key concept. We fix the scale factor. It is always changing because time is always evolving. Cosmic time, d of t, dt, that little thing is always stepping, but we're pretending we can stop it, okay? That's a big element of this idea. Next, this allows us to be really quick because if without that, we only have two terms, A of t dr and ds. So then we can take the square root of both sides, right? And then we've got a very, very, very simple expression, and that is d of s, meaning is a function of A of t dr. So we had to fix it in time, remember? We had to pretend that we could fix the distance in time and do layout meter sticks. That's what we're doing. The definition of proper distances, pretend that we can stop the universe from expanding, and then lay out meter sticks to that distant galaxy. That's all we're pretending. That's proper distance. So when you measure a distance on the surface of the Earth with a meter stick, going back and forth with something, reflecting sonar or whatever, you're measuring the proper distance. And this is the cosmological version of it, which is simply specifically states what the definition is. And that's all it is. We then give that a special name. And, you know, why is this important, right? Because the universe is expanding. So why are we bothering with this? It does matter. It actually does matter. So let's use it as a tool, which we will use later, okay? So we define the proper distance to be, if we fix it at a particular distance, and fix the scale factor at a given time, lay down those rulers, what would that distance be? That's the proper distance. So we call that d sub p at a given time, not as a function of time, because time's not changing. So this is kind of a weird notation, right? So it's d of p at a given time. So we should probably have some weird way of saying that it's at a time, right? So, but d of p is simply equal to this co-moving distance r, which is not fixed because it's not co-moving, because it would be co-moving r if the universe were expanding, but it's not. So this combination of A of t times r becomes the proper distance. Okay, so what does this mean? We now have a bunch of different kinds of distances that we can talk about. We can talk about the proper distance when a galaxy was nearer and when it is now farther. So light gets emitted by galaxies. What was the proper distance at the time the light was emitted by some star, by some process, by a distant gas cloud or whatever, stuff falling into a black hole and going eek at a time? You could say, what was the proper distance at that time? And that's the bottom blue arrow that goes across the bottom. Now, as time goes on vertically, moving from bottom to top, that was the time of emission of that photon. As that goes, it travels towards us in time. And so the time goes up, the photon eventually gets to us, it gets redshifted, that's what's happening. And the proper distance of that galaxy is now much larger. The proper distance today of that same galaxy is now much greater than it was when the time of emission, right? We pretend we freeze it again and now measure them again. The proper distance is now bigger. Now, if you look closely, there's an arc. The photon goes on that funny arc, but the light travel time distance is not the distance that the light traveled, because the light traveled along that curved trajectory while we simply traveled through time, right? We were fixed, right? Our little galaxy is just going from bottom to top. The distant galaxy is curving off to the right as the universe carries it away, and the photon is kind of going against the current like a fish going upstream, right? But we can then say how far did the photon travel by saying it was emitted at this time and we received it at the later time. And that is the distance that we say when you read in some newspaper or online and say, oh, this galaxy is 13 billion light years away. That's what they mean. That is the distance in light years. That is exactly what they mean when they talk about it. They're not talking about the proper distance. They're not talking about the proper distance at time of emission. They're not talking about the proper distance at the time of the photon's reception. They're simply saying it was emitted at this time and was received at this time. Now, remember, photons don't carry clocks. So this is why the light travel time distance is kind of meaningless, because you should be saying to yourself, well, how do you know it started then? Right? You should be saying, well, how do we know it started back then? And the reason we know is because of the redshift of the photon. We know the processes that would have emitted the light, and we know the spectrum, because it's not just one photon. It is a whole spectrum that we gather. So we find the spectrum of the galaxy, which is a combination of all the photons emitted by the galaxy, and we see the spectral lines of hydrogen. We see the spectral lines of helium, more like hydrogen. So we see the Balmer emission lines, which are the brightest emission lines, and they're redshifted out of the ultraviolet and down into the red. Yeah, so that's how we know the distance, is because of the redshift. And the redshift occurs because of the expansion. And then we say, for public purposes, so that people can understand what the heck we're talking about, we then translate that redshift distance into a light year distance. That's what we do. So there's a little bit. How's that bite you? I want to see. Does that make sense to you guys? Any comments, emoji, stuff like that? While I take a break and have a little bit of my soba chop. It got cold. I've been talking a lot, haven't I? Yeah. Cat's sleeping. That's all that's important. He's right there. All right. See, he's right there in the chair. Chair behind me. He likes listening to me talk. Okay. So great. Fantastic, Catherine Jane, 1784. Fantastic. So yes, should I go grab the cat? He deserves some time. Hold on, let's take a break and grab the cat. He's not gonna like it, but that's just life for a cat, right? Here he is. Just stir the cat. There he goes. There he goes. There's the cat. He's gonna give me a bite pretty soon. There he goes. Very good, buddy. Cosmo. Cosmo C cat. Very. C, of course, stands for cat. Fantastic. Okay, let's keep going. So that's what we mean by light travel time. So light travel time is not the distance that we really ever care about in cosmology. That is an irrelevant thing. It belies the fact that we actually had to translate it from redshift distance into light travel time distance so that people can say, oh, I kind of get that, right? That's what that's about. So what do we mean by all that stuff? What we want to look at then is take that proper distance and translate it now into a series of steps that go from when it was close to when it was far. And our mission is to find out how fast the universe is changing its size, okay? So we've actually kind of completely covered what Ryden was wanting to get, which is the proper distance. But we need to get at how we get to a proper distance and how we can possibly even use that thing for anything. But what we can say is, even though the universe is being considered to be frozen at that time, the universe has a given size scale at that time, right? But we can also say, given that we frozen it, how fast was it expanding at the moment we froze it, right? So the universe is expanding universally, homogeneously, and isotropic everywhere in the universe all at once. So the rate of expansion is the same in the universe, in the same way that the scale factor is the same everywhere in the universe at that moment you freeze it. So we're going to use the dot notation for derivatives, time derivatives, meaning time derivative is simply a rate of change of distance with respect to time. That's what speed is. How far am I going in a unit in some distance, in a unit of time? So dp dot of time is now the proper velocity or proper speed, right? And that's the same as the rate of change of the scale factor times r. Now the r doesn't get a time derivative, okay? And the reason the r doesn't get a time derivative is because it is a coordinate distance. The coordinate distance doesn't change. Remember, we had on a ruler ticks, ticks on a mark. Yeah, he is a beautiful dude. Yes, he is a sweetheart. He is a very good sweetheart, and he's giving me a good bite because I play with his toe beans right in the chair. Ow, ow, buddy. He said, "I'll bite." Anyway, so yes, Cat will make more appearances in future videos. So, where was I? Okay, so what we have the scale factor changes because that's the thing that's changing. But r is like how many ticks are there on a standard ruler. On a standard meter stick, there are 100 centimeter ticks and 1,000 millimeter ticks, right? Just because the meter stick is expanding doesn't mean we add more ticks. The ticks are simply the tick marks on this thing. The scale factor shows how far apart they are, right? We called it a millimeter, but a millimeter is the distance between two ticks. Now, what if it grows in size? The denotation of the millimeter will still be the same. It is a milli, 1,000th of a meter, but now the meter is scaling. That's what the a dot is. It is a scaled meter. Weird idea. So r is a coordinate. It is the tick on the stick. It does not have a value associated with it. Only the a dot gives it the value. The a of t gives it the value. And that a of t is changing. Now, from our definition before of what r is, that's simply the proper distance divided by the scale factor, right? That's from a previous slide. So we just plug in for r what the definition of r is, which is the proper distance divided by the scale factor, keeping the a of t. I'm dropping the paren t notation just because it's getting confusing. And then I rearrange it to say a dot over a. Both of those, of course, are still functions of the fixed time times the proper distance. So the rate of change of the proper distance is equal to this thing that involves scale factors times the proper distance. We now redefine the rate of change of the scale factor compared to the scale factor as h of t, or the Hubble parameter. The Hubble parameter is the thing that shows the change in the proper speed change compared to the proper distance as a function of cosmic time. So what is the definition of the Hubble constant? So if we set that moment not to yesterday, not 2 years ago, not to the future, but to today, roughly-ish, and when it was discovered in the 1930s, it's the same as now for cosmology. That moment is today, and the Hubble constant is therefore h of naught, which is the t of naught of today. So when we say naught, that's sub-zero, that's the thing that says now. Now that t could be any time, but we're choosing now when we are talking and thinking about cosmology and stuff. And Cosmo is in the chair. That is now. So we can now say, how fast is the universe expanding now? How far away are things now? If we continue to freeze things, right? But the distances between galaxies are expanding right now, but we'd have to wait a long time for them to actually have a change in distance for us to actually, quote, measure a proper distance change. So we have now attribute this, we now know that almost all galaxies are expanding away from us. The Andromeda galaxy and the M33 are mutually bound to us through gravity, and so they're falling towards us. That's what the velocity shows in the redshift, blue shift, I should say. And we will collide with them in 5 billion years or so, and that'll be an interesting sight, as it takes a billion years to actually resolve the collision. But everything else is receding away from us. And so the Hubble parameter, the Hubble constant, shows the rate of expansion of the entire universe today. Okay. Next, then, we can then define a very, very important distance using the Hubble constant. The Hubble distance, or the horizon distance, is the speed of light divided by the current Hubble parameter. See, we can have it because we had a speed here, v sub p. So that's a current speed. Set that speed equal to the speed of light and divide by the Hubble constant, and you get the horizon distance. How far would you have to go with rulers to get to the place where the rate of change is the speed of light? That's what we mean by the Hubble distance, or the Hubble horizon distance. And that is a far distance, right? The current value of that is large. And if you want to have some fun, divide it out yourself, assuming a 70 kilometers per second per megaparsec. So let's then okay, but I'm going to go back just a second. The horizon distance is an incredibly important element because it shows the boundary of things that can have possibly interacted or influenced everything else inside of a Hubble distance. We call it a Hubble distance, a horizon distance, and everything inside our horizon distance centered on us and Cosmo is, well, Cosmo's the center of everything, of course, because he's a cat, right? Aren't you, buddy? Yeah, he's now looking at me and he's looking at the camera. That's hilarious. So the horizon distance is a huge volume centered on us, right? Now, you go a billion light years to the left, that horizon distance includes us, but it doesn't include some of our sky, right? That would be a loss of a billion years this way because we went over that way, right? So every location has its own horizon distance. And so you could keep stepping over and over and over and say, how far do we step to get to the end? Well, there is no end because we don't believe at this time that the universe has a finite size. So we could keep finding Hubble bubbles, these Hubble distances centered on a galaxy, and just use the TARDIS or something else or magic and go from here to here to here to here and just keep going and going and going. Where does that stop? It's turtles all the way down, as they say. It just goes on forever. So our horizon distance is not the size of the universe. We do not know what the size of the universe is. But if the curvature of the universe is flat, then the universe is infinite in extent, and we can do that little translation as many times as we want, as many times as we're able, and we will never stop. But if the universe is closed, meaning it has positive curvature, then if we did that, we just kept translating around, we would eventually come around to meet where we exited. If the universe has a negative curvature, then it's even bigger than a flat universe. And we would find ourselves getting farther and farther and farther away from other bubbles as we stepped in straight lines. Not just like linear like this, but it would be more like that. They would diverge quickly. And that is a negatively curved universe. The current hypothesis is that the universe is flat. That is the standard concordance cosmology, which is under some challenge, but so far it's mostly, most challenges have failed, and it's a concordance cosmology, irrespective of the Hubble tension that is occurring today. Okay, next. Wow, I've been going at this for an hour. Wow, I better have water. I better drink some water here real quick. I can't believe I talk like this. Hubble bubble. Yes, a Hubble bubble. Hubble bubble hops. Hubble bubble hops. That could be a great name for a beer, right? I would like a Hubble bubble. It's a very hoppy IPA. The Hubble bubble IPA. Okay, next. The Minkowski versus the Friedman, Lemaitre, Robertson, Walker spacetime. Hubble bubble IPA. I want some. Actually, I stopped drinking a long time ago, so you go make it. I give that idea to you to go make money. Please do make money in these times. Someone should make money. You can't get an AI bot to make beer. Okay. So in our world today, we can think of we could think of having a Minkowski spacetime, which is a non-expanding spacetime, right? That's just distance times time in a Minkowski spacetime metric, meaning you're going fast, and that the Minkowski metric is a flat spacetime metric, not expanding flat spacetime metric. So you could lay down rulers from galaxy A to galaxy B, and they wouldn't move because Minkowski spacetime, which is the special relativistic spacetime, doesn't expand. But if we then add dynamics to the spacetime, meaning there is a change in the overall spatial portion of the metric with the AFT. Now, this is a reformulation using this particular metric, but you might also see other, the conformal time metric, which folds the AFT into the time as well. So you could have different kind. You can have the same kind of metric, but in different coordinate systems. I'm just choosing a peculiar coordinate system that keeps the spatial, that keeps the scale factor attached to the spatial portion of the metric. But we could easily redefine what we mean by time and call it conformal time, and then have the expansion also affect the time component too. And that's a common usage in cosmological textbooks. But the FLRW metric is a dynamic spacetime. So as we traverse from left to right, and that is a time change, not a physical location change. We're standing still in this thing where it's guy's here and then he's there. He's not walking from left to right. He is standing still and time is passing. In that case, then the galaxy is moving away. And in the same cosmic time, it has moved a different distance because the universe is expanding. And so it carries it along. From our perspective, we don't move in space. So therefore, we don't have that. Now, if you were to translate yourself over to that galaxy, they would be symmetric backwards on us. We would look like we're expanding away from it, and it would be standing and going simply that staying put. So that trapezoid that you see, if we translated ourselves to that distant galaxy and looked back at us, it would be translated the other way. We would be falling away from it. And that's the nature of a dynamic spacetime. The current horizon distance, fun stuff. The Hubble tension is kind of is batting us about with that, and it's wonderful. The current thing is roughly about 70 plus or minus 2 kilometers per second per megaparsec. This was tighter a long time ago, but yet the difference between the cosmic microwave background and the baryon acoustic oscillation measurements compared to Cepheid variable measurements and supernova measurements, these two things are in very, very, very great tension. And the measurements are significant enough that it is an active and a very important problem in cosmology. And it's been around long enough that people think that this is going to reveal some sort of new physics. But it doesn't change the fact that the universe is expanding. It also doesn't change the fact that the Robertson-Walker metric is probably the right thing. There might be some inhomogeneities that pop up to make it not a perfect metric for the entire universe, and there's some debate of whether or not that's true. So some sort of new physics is probably in the offing, but a lot of cosmologists will aim to be tweaking the parameters of the universe, as opposed to other people who say, I would rather tweak what stars do and what galaxies do and what that whole extra cosmological distance ladder is doing, because there's lots of sources for error. So tweaking it out of there is very important. So the current horizon distance with the Hubble constant at 70 gives us a distance of 4.3 gigaparsecs, which is, I mean, let's translate it to light years, even though we shouldn't. So 4.3 gigaparsecs is approximately 14 billion light years, right? So we're keeping with the megaparsecs because that's an actual physical distance that we would use. So that's our horizon. Anything within 4.283 gigaparsecs or 4,283 megaparsecs, that's within the area that could have affected us in the past, right? That's what that's what the horizon distance means. So now let's link the metric to the redshift. And that's very important because the redshift is a physical measurement we get. We gather all sorts of information starting from the parallax and using all these little steps to get out there and use the redshift, but we want to link the redshift to the metric of space-time, because the metric of space-time contains the scale factor changes, it contains the radius of curvature of the universe, it contains the curvature style of the universe. So we have to link the redshift to the metric so that we can understand how we measure the space-time itself. All right. So again, we use that simplified version of the Friedman, Lemaitre, Robertson, Walker metric, and we say light always travels on null space-time metrics. That's what we learned from special relativity. It does not change in general relativity. So for photons, ds is always 0. And if it travels in a straight line from there to here, we don't have to worry about the omega portion. So then we have for a photon, or a group of photons, or a string of photons, or a chain of photons, we have that very simplified version of the metric. 0 equals the speed of light times time, plus the scale factor times the coordinate distance. Okay, we are now letting time change because we want to see the effect of the universe through time on a photon. So now we're going to let that time change. Rather than fixing the time like we did to get the definition of proper distance, we now let it change because the universe is evolving, because that photon travels a long distance. So now we're going to play a magic spell. Ready for it? We take that thing and we rearrange this whole little fun equation, and we simply get rid of the 0, put this minus on the other side, and divide. So we have the speed of light times dt, which is a change in time, divided by the scale factor, is equal to the coordinate distance time. The coordinate distance, not a physical distance, but a coordinate distance. The scale factor gives the coordinate distance real distance. Okay, off we go. And now what we're going to say is that we think about photons that are emitted. Remember they had that little cartoon of galaxy emitting light, and it comes from there to here. So we want to see that curved arc that I showed way back up here in slide 22. We want to see this curving arc. We want to see what that is. We want to see the effect of that. We don't care about this. That's the light travel time. We want to know about this arc. So back we go over to here. So we integrate every single little step from here to there, the time from the emission to the time of observation. And from the photon's perspective, it starts at its point 0, and it goes a coordinate distance r, right? And that's all mediated by the speed of light, c. So we want to integrate that time. And the integration means we lay down the meter sticks, right? How many meter sticks is it? That's a sum of all the meter sticks. What is a photon? So now here comes a very interesting thing. A photon is a wave packet. It is the electric field created by the motion of charged particles. And the charged particle was accelerated, shaken, moved in a non-uniform way, and that created a photon. There are lots of ways that the universe creates photons. You are looking at them now, and they're emitted in so many wonderful ways. But it basically comes from the change in an electric field in some material source, and then some electron moving with respect to an atom. It is a way, it's a very easy way for photons to be created. They can be created in lots of ways, but that's an easy way. When this thing vibrates, so you've got the electron zooming around the hydrogen atom, and it might be in a higher orbit, and then it drops the orbit, right? When it does that, that's a quantum drop from one level to another. That has a particular energy amount signature, and that can be translated, that energy amount is translated into a frequency of the photon. So we know that photons have particular frequencies for light, and that frequency is also its wavelength, and the wavelength can be described by a packet of increasing and decreasing intensity as it arrives, as it goes from here to there, and it goes into something. It gradually shakes the thing, the receiving object, and it carries a wave of electromagnetic energy. That's all it is. It's a wave packet of electromagnetic energy. And the wave packet has a wavelength inside it. So the photon, which is a very small thing, has a wavelength. We can think of it as having peaks and troughs, just like any other wave. And the green arrows show the distance between two of these wave peaks. Now, of course, as it travels, those waves go up and down, and they just kind of go from zero on the right, and then they get big, and then they get little. So the disturbance is what's traveling, not this little packet. So we can think of the white boundary as moving along. And as it moves along, the dots are pulled up and down inside it. It's not like it's a cell or anything, but it's the boundary of the disturbance. Because if I didn't put the white there, you would just see the dots, and that wouldn't look as cool. So I'm making a little bit of an artistic judgment by allowing this to have a little white boundary, but the photon does not have a cell or a boundary or a casing to it. So that is what's deceptive about my diagram. But hey, let's just let it be, because it's a helpful diagram to your eye. And we can think of it as a packet of waves. As the universe moves along, as the photon travels through the universe, that photon packet gets stretched because it has a finite size, and every size gets affected. It's just that the photon travels such a large distance, and the sum of all the tiny changes to the space-time metric affect the photon as it travels this enormous distance. It's not just traveling down to the store to get some food at Whole Foods. It's traveling billions of light years, millions and millions of light years, and the accumulation of all of the little tiny changes in space-time affect the photon. So what is that expansion? We can then say, from the time of emission to the time of absorption, we want to see the difference in length that happens to a single photon. So what we care about is we're interested in the exact, not the first wave crest, which is the one on the right, the middle wave crest. We want to look at the next one. So we have two wave crests, right? The first one on the right, which the red arrow is pointing at, the first red arrow on the right, and then there's the second one, which is one wavelength after. So it experiences the same thing as the first one does, but it does so a little tiny bit later, right? Just the tiniest amount later, and that's what the boundaries of the integration are showing. Next, we then compare those two successive wave crests. We have two successive integrals. The bottom one is the right-hand one, the wave peak that is going first. The second wave peak, the top one, is the one that is coming second in the wave packet. Those are our two wave crests, one after the other. They're experiencing the same physical change. So what can we do? What we're going to do is we're going to subtract these two, right? We're going to subtract one from the other. And when we do that, we find that we notice that on the right-hand side, they're the same, right? Because they experience the same coordinate change. They experience the same distance that they arrive. So the right-hand sides of the equation are the same. So we set these two things equal, and that's what we get here. So since they're equal, we set them together. Now, the we can find that, we'll notice that the scale factor is still inside the integral, but the change that the scale factor does at a given time for a given wavelength is so small that it's constant inside this very short time period given by this integral. So notice it's going, we got rid of all the stuff that goes from beginning to end as well. So we're only looking at the time of observation to the time of emission between two wave crests, right? From wave crest A to wave crest B. T emit goes from one wave crest to the next. So we're seeing the effect of the entire thing on two successive wave crests, and all the other effects are being taken away. Let's go back a bit, because I think I kind of glossed over that not as well as I wanted to. Notice that I've kind of skipped from this integral to that one in kind of a weird way. We can add the two, if we subtract one interval from the other. If we subtract the bottom from the top, the right-hand side is 0, and the left-hand side gets rid of everything up to T observation. And the left side also gets rid of everything up to T emission. So we're only left with the distance between, the time distance between T emit and T emit plus the emission wavelength, and T obs to T obs plus the thing, when we subtract the bottom integral from the top and rearrange to get this. Hope that makes a bit more sense. Because we have these two integrals, we subtract the slightly bigger one from the slightly smaller one, right? Or yeah, slightly smaller one from the slightly bigger one. And that's what we have left over. And it only has this very tiny interval between the time of observation of one wave crest and the time of observation of the exact next wave crest. And then we have, on the right-hand side, the time, we're looking at the time interval between the time of emission of the wave crest and the time of emission of the exact next wave crest. For a photon, that's a very tiny amount. So therefore, that extraordinarily short period of time, the time between two individual wave crests, one at the beginning and one at the end of the journey, the scale factor is identical between them. It's approximately the same. So it's so much the same that it might as well be the same. So we call it the same. And we've determined that the observation, we can pull that out of each of the integrals for that given time. The scale factor at the time of observation for this photon, we're looking at the left-hand side of the integral, the scale factor at time of observation is that scale factor when it was emitted. And the boundaries for the integral are very small. That's a very tiny emission, because lambda sub naught over c is the wavelength of the next, is the distance to the next wave crest. Likewise, on the right-hand side, we have the scale factor at time of emission, and the integral runs between the time, a very small time interval that has a length of the wavelength divided by the speed of light. That's a tiny interval between them. Now the wavelength has changed between the two. So only the boundaries matter for the wavelength change. What's left in the integral is only this tiny difference between two boundary values, the time of emission and between, it's just an extremely small wavelength time. And the time obs plus the wavelength minus time obs is the wavelength at that 0 divided by c. So we can simply reduce the left-hand side integral to lambda sub naught over c, and the right-hand, that's lambda sub naught is observed, and on the right-hand side integral, that reduces to the wavelength at the time of emission divided by the speed of light. Speed of light is constant on both sides, so it can be removed. And we're left with the wavelength of time of emission divided by the scale factor of the universe at time of observation, and is equal to the wavelength of time of emission divided by the scale factor of the universe at the time of emission. Okay, this is interesting. We have now linked the scale factor and a measurable. The measurable is if we do know the nature of stuff. We know that hydrogen atoms exist. Let's say we know that atoms of hydrogen are in the universe. The spectrum of hydrogen is well known. If the laws of the universe are the same way over there as they are over here, then the wavelength spectrum, the spectral features of hydrogen are universal. And it's the same there as it is here. So we know what the observation is because we can find the pattern in the light of the wavelengths of hydrogen in a distant galaxy. And that gives us our Landis knot. We now know that this thing once was this wavelength because, or this, we're not just talking about one photon anymore. We're talking about a whole spectrum of photons. We have to get enough photons to describe the entire spectrum according to distinguish it as hydrogen, right? And once we know that, we got everything. Because now we know that was hydrogen. We know what its original wavelength was. We know it was 512 nanometers. We know it was 3652 nanometers. We know what the wavelength of that hydrogen was when it was emitted, when it was originally emitted, and we also know what we observe it to be. So that is how we use the wavelength. We don't do it for one photon. We do it for a spectrum, and we look at the entire spectrum being shifted. And that gives us the redshift. So the very definition of the redshift is the observed wavelength divided by the emitted wavelength. We know what it was we observed, when it was, what we observe it to be, and what it was when it was emitted. It is shifted by the redshift, which is 1 plus c, and that is equal to the ratio of the scale factors. You hear Cosmo? He is telling me things. He's saying that I should get done soon so that I can feed him. I will have to do that soon. Can't play all night, guys. So here we go. So this is the way we link the observed to the emitted wavelengths of light and get related to the scale factor. Again, we go back. Come on up, buddy. Come on. Gotta take a second. Come on up. He's not coming back. He's not going to do that. He's just going to howl. Let him howl. I'll feed him in a little bit. Don't worry. He gets lots of food. Nice white food, Tiki cat food. So what we have now is we're going back to this wavelength of time, and it shows us that we can link the dynamics of space-time to the space-time, to the scale factor A of t. And how does the redshift then measure the expansion? If we have a blue triangle that starts at all these sides, oh, I think this is nicely animated if I remember correctly. Let's see if I got it. Can you? I don't know if you can. I'm going to assume you can. So I'm going to just exit out. Uh-oh, crashed. So each of these sides is the scale factor at an early time. It expands at a later time. Maybe it grows by a factor of 2. And we've labeled them so that they have a particular size. It has grown. And the scale factor for the triangle grows by each of the scale factor for each side has grown by the same amount, preserving the relative size of an orientation of all of the angles of the triangle. And if we choose, the measurement redshift then does measure the scale size distance. I'm just bruising through this really quick. Without loss of generality, we can look at only one of those sides. So we now are getting to the point where we have a distance of a side of a triangle, or a length between, say, something here and something there has expanded. And we only care about one because because the entire universe is expanding. It doesn't matter which orientation that triangle is. We can look at one of those sides, and we can take the rate of change on those sides. And that gives us, we're having a time derivative, or the speed with which the sizes are changing, right? And we can change dot notation for ease of reading. And that gives us the speed equals the rate of change. The rate of change of the distance is equal to the scale factor change times the distance of the end result, the original. So these two things are equal. We set them equal. And we have the velocity of recession of a distant galaxy is related to the scale factor. And this is basically a retelling of what I talked about before. We end with velocity as a function of distance, the equation. We saw this actually earlier, and I might just cut this from the next thing because we're back to this again. The speed with which something is receding is equal to the Hubble constant times its distance. Gosh, the cat is really telling me stuff. And that is the cosmological principle in action. Importantly, very, very, very importantly, is that this triangle concept where we take a shape and expand it, no matter how we do it, the orientation can be on flat like this, it can be rotated, it can be at any location, translated left and right, rotated by any angle, and this triangle would be deformed in exactly the same way as the universe expands. It doesn't matter where in the universe this triangle, the blue triangle is, later it will be expanded to the green. It doesn't matter where or how it's positioned. And that is the cosmological principle, which says that every location in space is the same for all laws of physics. So the Friedmann-Lemaitre-Robertson-Walker metric is a dynamic spacetime, and as the universe expands, the photon travels along. I hope I can get this. Maybe I can just force it to do it on this. I think I'm sharing the whole screen, but I don't think I can actually make the animation work. Oh, sad. Can I just do that? Oh, I don't know if you see it. I don't. So as it expands, the wavelength of light gets stretched. Much more importantly, as I alluded to earlier, everyone has their own observing horizon. We could be looked at as the yellow group in the center of the yellow Hubble bubble, right? But there's might be distant observers in the blue and the red and the purple. As our universe expands, as the universe expands, the others are taken away. But every observer has their own horizon. And so the blue observer sees us within their horizon, but they don't see the red and the purple. The purple sees us, but doesn't see the other time. Hey, good to see you, Frozen North 32, 34, 26. Good to see you. And the red has us in there, but not the other two. So there are three overlap. The Venn diagram of universes and Hubble bubbles. Where do they end? And what about the green guy over there? And what about somebody, a different one, farther and farther? Where do all of these horizons end? And the answer is 1, we do not know, because we don't know the curvature of the universe. We think right now that it is flat, meaning there is no curvature. If it was positively curved, we could say, well, it'll end at some point because it's a closed universe, and that's that. But an open universe or a flat universe means that this process goes on forever. And if it's the universe, then there would be packets of Hubble bubbles over and over and over and over. Now, here's the funny thing. For our universe, I think you can see my mouse on this thing. I hope you can. Oh, good. Our boundary for our universe, or our Hubble horizon, is here. And this is the location that we see the cosmic microwave background. Yes, it does. It does actually boil down really quickly. The boundary that we see is what we think of as the cosmic microwave background image. So this Hubble bubble that I'm showing you is where we perceive or measure the cosmic microwave background to be. But every one of these observers sees the same thing, but with them at the center, right? So that means the cosmic microwave background is everywhere. It's everywhere. It's not just at that boundary. It's where we see it to be, because that's where the light, that's the distance from which it came to us. It finally reached us from there because the universe is expanding and trying to pull the photon back, just like a child running up an escalator, or on that walking thing on at an airport, the walker helper. It pulls the photons away from us and they eventually get to us. So where do all the horizons end? Currently, we don't think they do. The proper distance, which here we now say is the Hubble distance there, that is the proper distance to our horizon. The proper distance is the thing that helps us understand the nature of the redshift It helps us understand the expansion rate, and it helps us understand all of is our fundamental concept for distance. We will get to other distances later in future lectures, and how we actually use these distances to calibrate the scale factor, the radius of curvature, and the curvature type. And the best thing about this is that sometimes people say, wow, what's going to happen to us in the future? Are we going to get pulled apart and such? Cosmic expansion is only really relevant on the largest size scales. We have to get out to millions of light years or kilopart or megaparsecs before this effect is perceivable. Otherwise, it's not perceivable. But as we get larger and larger size scales, we look at the lower right-hand corner, which is observable universe, which indicates an isotropic, homogeneous universe with all of the laws of physics being the same everywhere, meaning every observer would see the universe very similar. But those previous other people, that distant green guy, might one day see us, but right now they don't. All right, I've got to go feed the cat. Thank you so much for watching. This was actually simply a practice for me. I haven't done this in a while, and I wanted to kind of go through this just to get my chops down and see how I sound and stuff like that. And maybe I'll do another one of these live things, because this is like class, right? You know, it's kind of like going to class. And you know, Cosmo is quite a student, I would say. He makes things happy. So I don't know if I'll do this in the evenings, or maybe I should do this on weekends. What do you think? Well, yeah, you think that you get the cat sounds? Great. You can hear him? I'm glad you can hear him. I got to go get him. I should bring him around. You know? So Cosmo will definitely be part of the future of this channel, because he is a worthy cat. Thank you, Marie Neptuno. If you haven't done this in a long time, you can go back and look at the cosmology videos that I did record before and get yourself all the way up to this part, because this was kind of a free-forming sort of thing. It's the kind of way that I taught when I was at college. Oh, great, thank you. Yeah, I've not tried to do live streaming with this, so yes, astrophysics plus cat sounds, right? Exactly. It's wonderful. So okay, I'm over here reading this. I've got to set up a better deal, because I've got a junky camera there. I've got a really good microphone over here, but I haven't hooked it up. I'm just using stupid YouTube streaming. I haven't gotten a proper streaming setup, but hopefully this all sounded good. I'm just using standard Mac stuff and standard. I mean, this is just simply monitor here and a MacBook Air of all things. Geez, the things you could do with a quiet room, a cat, and a good computer. So anyway, thank you for joining me. I'm going to go feed the cat, and have a great night. Take care. And like the channel, please. Also, go watch videos, so get those numbers back up, because, you know, it's been light. Take care. Have a great night, everyone. Bye-bye.